Hubble moved on to a second target, the Aristarchus crater, 25 miles wide and about 2 miles deep. Created by an impact just 450 million years ago, a short time in cosmic history, it's one of the youngest large features on the Moon. That impact exposed the ground below, and with it, the history of a region rocked long ago by impacts, volcanic explosions, and tectonic shifts. This region, too, is rich in ilmenite, and therefore oxygen. But what about the other element in water, hydrogen? In 1998, the Lunar Prospector, an unmanned satellite, began an ambitious mission to map the lunar surface. With an instrument called a gamma-ray spectrometer, it recorded the telltale signature of a variety of elements. The data showed that hydrogen is spread widely across the poles of the Moon. If it's from water ice, millions of tons could well be embedded in the soil there. And there's one place in particular where water may be concentrated. The Moon is in what's called tidal lock. Only one side of the Moon faces the Earth, and yet, as it orbits its mother planet, all sides are bathed by the light of the Sun, instantly evaporating any water that might get to the surface. Still, there are places that never receive direct sunlight. The floors and sides of deep craters. These shadowy areas, found mostly around the poles, may well contain stores of ice. One of the best places to look is at the South Pole, especially the famed Shackleton crater. It's named for the fabled explorer of our own South Pole, Ernest Shackleton. If there is ice here, it might have been delivered by the asteroid or comet that hollowed out the crater in the first place, or by others which impacted in other places, spraying vapor that came to rest here. As important as it is, water may not be the only vital resource for future explorers. Back in July 1969, astronaut Neil Armstrong departed slightly from the mission plan. He scooped up some dirt, known as regolith, used it to fill out an empty space in a sample container, and brought it back to Earth. The dirt had been lying there for millions, if not billions of years, soaking up the Sun. Scientists found that solar winds had endowed that dirt with a substance rare on Earth called helium-3, and there's a lot of it there on the Moon. So now, Chinese, Russian, Indian, and American planners are all considering ways to mine helium-3 as a potential fuel source for interplanetary travel and even large-scale power generation here on Earth. When people do return to the Moon, the poles may offer the best chance of finding water. But try landing there. The light is dim, and sharp shadows turn the ground ink black. Engineers at NASA's Jet Propulsion Lab are working on special sensors to read the landscape and safely guide lunar vehicles to their landing sites. One of them is called LiDAR. It's a laser that emits pulses of light, 8 times per second, to produce a 3D picture of the surface below. On the way down, automated navigation systems will be programmed to avoid rocks and the slopes of craters to find the smoothest places to set down. The job of scoping out safe landing spots now falls to NASA's Lunar Reconnaissance Orbiter in the most ambitious lunar mapping project to date. Like a lunar spy satellite, the LRO is scanning the surface of the Moon with a multitude of instruments. It uses a laser to survey the topography. When the light bounces off the surface and returns to the orbiter, its timing and intensity reveal the location of steep slopes and rough terrain, or of level landing spots. Another instrument records the temperature. Where there's lots of loose material, temperatures change more slowly from day to night. So a thermal map can show places where the ground is too rocky or too soft for a landing. Finally, the orbiter trains a high-resolution camera on the surface. This allows mission planners to actually pick out any large boulders. In this simulation, the red areas are clearly unsafe, while the green are smooth and free of hazards. Few places on Earth have been scanned so thoroughly, and within the data, planners hope to uncover places that are not only safe, but worth exploring. Some say that past missions have only scratched the surface of the Moon. The LRO mission is designed to change that. The orbiter traveled to the Moon rather like a stowaway on a larger space vehicle known as the L-Cross. In October 2009, the L-Cross upper stage will separate, beginning a free fall toward the Moon. It's a 2-ton projectile aimed right at Shackleton Crater. When the upper stage, moving more than twice as fast as a bullet, hits the surface, it's expected to blast over 2 million pounds of debris into space and leave a crater at least 16 feet deep. The lower stage trails above and behind, equipped with a battery of infrared and visible wavelength cameras. Within seconds of impact, the lower stage will relay its data back to the orbiter, now passing overhead. And back on Earth, ordinary humans won't be left out of the action. Provided the sky is clear, astronomers will look on, with many wielding telescopes that Galileo could only have dreamed of using. With any luck, the orbiter and impactor combination will yield a definitive answer on how much ice is on the surface, how deep it lies underground, and what other resources call out to future generations of explorers and entrepreneurs. Until then, we'll have to content ourselves with images being sent back by the orbiter, like these craters thought to be strewn with lava that intruded from the lunar interior, or these more rounded features near the North Pole, or these incredible close-ups of Apollo landing sites, with shadows cast by the landers of Apollo 11, 14, 17, and others left behind when astronauts returned to Earth. "40 years ago, the Apollo mission showed that we could overcome Earth's gravity and set foot upon the Moon. But not for long. Now we are making plans to go again. Emboldened by evidence that we can find the natural resources to extend our stay and to extend our reach out into Galileo's solar system and beyond, into the wider world.